Hi, today we'll be talking about hypothesis testing with independent samples t-tests. And the question we're trying to answer is, who has a better sense of humor, men or women? This is the example discussed in the How It Works section of Chapter 11 in your textbook. I believe it begins on page 286, so you can follow along if you wish to. So the study that we're going to be talking about today, a group of researchers at Stanford University did some functional magnetic resonance imaging of men and women's brains to see what areas were activated when people were shown humorous stimuli. And their results indicated actually that women's centers of their brain where they feel happiness or they feel rewarded were activated more than men's center of happiness. And they wanted to make sure that it wasn't just that women viewed things as being funnier or men viewed things as being funnier in terms of a baseline. So this example is based on the results of the second part of their study. In our particular example, we're working with 4 women and 5 men. And they were shown a series of 30 different comic strips, and then they were asked to rate it whether they were funny or unfunny. And the scores that we're working with represent the percentage of cartoons that each individual rated as being funny. So we begin our hypothesis testing process with step 1, where we determine what the population is that we're working with, or populations in this case, the comparison distribution, and the assumptions that we're working with. So first is our population. We have population of men and their ratings of whether or not a particular set of cartoons are funny or not. And we have the population of women who are also rating cartoons on whether they're funny or not, and what percentage they rated as being funny. Our comparison distribution is a distribution of differences between means. Now, we get this name from the fact that we have 2 different samples, a sample of men and a sample of women, and we find the average of each of those samples, and then we find the difference between them. And so it's differences between means, whereas before we had a population that was a distribution of mean differences. So mean differences meaning that we find different scores and then we get the average. So in this case, we're talking about a distribution of differences between means. Now our third assumption, or our third step is the assumptions. Now you'll notice that these look very familiar. The first is that the distribution of means is approximately normal. And we can assume this pretty safely because of the central limit theorem if the number of people in our study is greater than 30. The second is random selection. Again, did we randomly choose men and women to represent our 2 different samples or not? And if we can't assume this, then we have to generalize with caution, which is why scientists like replication, because we can alter our samples a little bit to see if we can get the same effects. And the third one is the dependent variable is scale. And we do have a scale variable. We have the percent of cartoons rated as being funny as our outcome variable. So these assumptions are the same as both the z-test and t-test. So we really haven't learned any new assumptions so far. So if you're talking about comparing a sample to a population mean, or you're comparing 2 different sample means, then you're talking about the same set of assumptions. So the second step is where we state our null and research hypotheses. And in this case, again, we're going to be talking about a 2-tailed test, which influences the way that we write these hypotheses. You'll notice that for the null hypothesis, we're saying that sample 1 is equal to sample 2, which essentially says that men and women find the same percentage of cartoons to be funny. So there's no difference between the 2. It's kind of the boring one. And here we have our alternative or our research hypothesis, where we're saying that men and women find a different percentage of cartoons to be funny. And notice that we didn't say a particular direction. We didn't say that men found things to be funnier or women found things to be funnier, but that they just find a different percentage of cartoons to be funny. So the third step is finding the characteristics of the comparison distribution. Um, from step one, we know the comparison distribution is a distribution of differences between means. And for each type of distribution, we need to find those characteristics. The first part is finding out what we would expect our difference between population means to be if the null hypothesis were true. So what we're saying, if there's no difference between the two, is that we would expect these two population means to be the same. That is, the same percentage of men and women would find the same, men and women would find the same percentage of cartoons as being funny. So in this case, mu sub 1 minus mu sub 2 is 0. The most complicated part of the independent samples t-test is finding the variability of our distribution of differences between means. And it has several steps that I'm going to go over now. And this variability, this measure that we use, this is our denominator again in our t-test, and it's called the S sub difference. So it's the standard error of the difference. So remember, when we're talking about finding the denominator of a t-test or even a z-test, there's two parts that we need to work through. First is finding the standard deviation, and the second is estimating the standard error of what's going on in the population. So in our case, because what we have is two different samples, we'd like to use the information in both samples to figure out what the variability is and use that estimate of the variability in the population. Again, remembering that if the null hypothesis were true, then we would use that single estimate of the variability in the population. And then we use that to estimate standard error, which is the second part. So for estimating the standard deviation, for all t-tests, we don't know the standard deviation of the population. So we have to estimate it using all of our sample data. And for the independent samples t-test, this is called the pooled standard deviation. We actually spend a lot of time using the pooled variance. You'll notice that we're working with variances a lot more for the independent samples t-test. And the second part, then we need to estimate that standard error for the comparison distribution, which is the distribution of differences between means. We use the standard error is called the standard error of the difference. So the first step in finding our standard error for our test is finding S pooled. So we compute the variance for each sample independently. So we get a variance for men and a variance for women. So here we have our scores for women. We have the mean score for each woman. And we also have our scores for men and the mean score for each man. So here we see that we take an individual x, we subtract out the mean, we square those deviations. This should look pretty familiar. This is what you've been doing all along. So we get all of our set of deviations, and then we square those deviations, and we get the full set here. And then we add them together. That's our sum of squares, which is also the numerator of our equation. And we divide it by n minus 1, which is also our degrees of freedom. Notice that there's 4 scores here for the women, so 4 minus 1 is 3. And so we'll take the sums of squares x divided by 3, and you'll see that the variance of the women's sample is 289.584. Again, we'll do the same thing, but now for the men. And you can see we've found those deviation scores from the mean. Our sums of squares is 82.25. And here you'll notice that degrees of freedom is 4 because we have 5 men in our sample. So there's a little bit more information about the variance from the men. And so we find the variance for y to be 309.8. So then, in our next step, we found our variances. We've put them here. Variance for women, variance for men. We have to pool those variances together. Now, if our two samples were equal in number, then we could weight each one of them equally because we'd have the same amount of information in each. But in this case, we actually have 5 men and 4 women, and so these weightings will be different. This one will be a different fraction than this one to get our pooled variance. So in order to pool our variances, here remember the degrees of freedom for women that we found was 3. Our total degrees of freedom is the sum of the degrees of freedom for women and the sum of the degrees of freedom for men. So in our case, it will be 7. So 3/7 of the variance for women and 4/7 of the variance for men will be added together to get the pooled variance. So you'll see that we have 124.107 plus 177.029, and that gives us a pooled variance of 301.136. So you'll notice that it's somewhere between the two variances that we've computed. So that's our pooled variance, which we'll now be able to use in order to calculate our standard error for our test. So there's 3 steps in finding S sub difference. The first is that we need to convert that pooled variance to a squared standard error. So you'll notice this looks familiar, S sub m, but now it's squared. So this is the standard error, the squared standard error for women, and the squared standard error for men. And we substitute in our values, and we get 301.136 divided by 4, because remember, this is the total sample size for women. And here we have the total sample size for men. So we get each of those values. We've got our 2 variances, 75.24 and 60.227. And the other thing you'll notice too is that the men's is smaller. And part of that is because we have more information, so we can be more precise. The next part is that we add the 2 variances together to estimate the variance of the distribution of differences between means. So it's simply summing the 2 standard errors that we found for each sample to find the the variance of the distribution of differences between means. So if we add these 2 together, we get 135.511. And then finally, because we need to use a standard error and not a squared standard error, we need to take the square root to find the S sub difference. So we come up with a S sub difference of 11.641. Now from this point, we can come back and say, okay, we found our S sub difference. It's 11.641. This is the hardest part, is getting that S sub difference. The rest of it should look pretty familiar from this point on. So we have to get our critical values. We have our null and research hypotheses. We've selected a p-value of 0.05, which is also our type 1 error rate. And we know our total degrees of freedom is 7, which we found previously. So if we come over here, and this is our t-distribution table, we've got 0.05. It's a 2-tailed test. And we have 7 degrees of freedom, then you'll see that our critical value is 2.365. So we can add those then to our distribution, and we've cut off 2.5% in each tail. So if it's more extreme, our calculated t is more extreme than these 2 values, then we can reject the null hypothesis. So now we need to calculate the test statistic. So we know that the difference between the population means is 0. The S sub difference is 11.641. And then we have our 2 sample means of 82.25 and 82.6. Now just looking at this, you're probably already guessing that, yeah, this is unlikely to be significant. But let's test it out. So here's our formula. We take the difference of women minus the difference of men minus the difference of the population of men and women, which in this case is 0, and over the S sub difference. So if we substitute all our values in, we find that we have a t-score of negative 0.03, which is basically 0. There's no difference between the 2. So we find where that is on our distribution of scores. It's just slightly to the left of 0, and we make a decision. And in this case, we're going to say, well, it falls between our 2 critical values, and so we are going to fail to reject our null hypothesis. So we can make a decision, and we can say that men and women did not differ on the percentage of cartoons they rated as funny. And you see that we present it here in statistical notation. And so next time we'll be talking about z-tests, t-tests, and analysis